Hey, Katie.
Hey, Ben.
So I remember a long time ago you were talking about this huge project that you were embarking on around cancer research.
Right. So, my day job is a data scientist, but there was this big research project or government policy project, I don't know what you would call it, called the Cancer Moonshot that was being done through the White House. And we had the opportunity to help out on that a little bit. It was super cool.
Awesome. Let's talk about it. You are listening to Linear Digressions. Okay, so maybe just for people who haven't heard that episode, because that was quite a while ago, can you maybe give a summary of what the project was originally about?
Yeah, so the question for us was we're data scientists, we're not cancer researchers.
Right.
But the question for us was how can data be brought to bear more effectively in the fight against cancer? And so we had to kind of very quickly come up to speed on how cancer research is done, and then take that and mix it in with a heavy dose of our knowledge about machine learning, engineering the computer systems that you need to deal with these data sets, what kinds of data sets are available, how are people using them, how could they be using them, and sort of turn that into a set of recommendations for the vice president about how we thought what's a plan of action for making data more effective in the fight against cancer.
Right. It seems like data science still kind of feels like a new field in a sense. And it seems like there are a lot of areas of research, product work, all the kinds of stuff that we talk about on the podcast that doesn't necessarily really utilize the full potential of what data science, machine learning, all of that stuff has to offer.
Yeah, so there's been a lot of really good research that's been done around cancer, of course, and there's many different kinds of research. That was one of the things that made it really challenging to get a handle on this field, because you have computational work where they're looking for, oh man, all kinds of different, like pure computational work, like looking at various compounds that you think hypothetically could be effective against certain types of mutations or certain symptoms. You have basic research, which is looking at things like doing genomic sequencing and looking at cells in test tubes and things like that. Then there's clinical research, which is where you have hypothetically some new kind of drug or some new other kind of therapy, and you're actually trying it out on patients and the various stages that a therapy will go through towards getting approved by the FDA so it can be widely used. There's also population level research, so trying to understand what demographic groups are most affected by cancer. Are there certain economic factors that might be important? Where are people getting certain kinds of cancers? How does it affect people at different ages? All those kinds of things that you need to have an entire population to start to get your handle on. So huge amounts of data are being collected to study all of these questions. And so it's not that they don't have data science, although they might call it something a little bit different. But clearly, we still have over 1 million cases of cancer every year, and hundreds of thousands of people die of it every year. So, to a certain extent, a lot of that effort has been very successful. But in another sense, there's still obviously a lot of work to be done. And what part of that can we maybe address using data?
So in a sense, this was kind of like a meta study. Like in science, a lot of times you'll have studies where you actually go out and you do research and you collect data, and then you have meta studies which kind of look at the conclusions of all of these different studies, and you're not actually doing any new research, you're more compiling things together. So this is similar in that you weren't actually going out and collecting new data, you were looking at all the data that's out there and trying to draw good conclusions from that using new means.
Yeah, it was even sort of a meta study. So you can imagine that an individual researcher in cancer might say something like, oh, well, let's look into platinum-based chemotherapies and how those affect, stage 2 liver cancer or something. And then there might be a meta study that looks at many different kinds of platinum-based chemotherapies for liver cancer and compiles some, conventional knowledge about what the state of platinum-based chemotherapy for liver cancer is. I don't even know if they use platinum-based chemotherapy for liver cancer. This is just an example, but you get the idea. Mm-hmm. But the point is that that's still kind of a narrow view of things. So the way that we actually ended up doing this research was we read some papers and and went through some slide decks and those sorts of things. But the bulk of the research was actually talking to people in the cancer field. And they were people within the cancer field who I don't think talk to each other that much because it's just such a huge field, or not all of them talk to each other. So we after a certain point, I think, had a much broader view, not as deep of a view, certainly, but a much broader view than most people who work in cancer about what's going on. So we talked to researchers at various cancer centers, at academic institutions. We talked to people who worked in the data infrastructure and how do we actually compile and maintain these data sets. We talked to the registrars, who are the people who maintain the population-based studies. We talked to patients. We talked to insurance companies. We talked to hospital administrators. We talked to lawyers, actually. A significant part of what's going on around cancer data is legal. It's not technical. And so from all of that, each of those people, has some idea of course, they know their core area of competency, and they might know the areas of competency that are most directly adjacent to it. But I think we actually got a really interesting set of perspectives talking to such a broad spectrum of people and starting to tie together the common themes that arose again and again, because then as you're talking to these people and you're getting their input on what's important and what do they think the field needs in order to use data more effectively, there are certain things that just come up again and again in those conversations. And so if it keeps bubbling up all over the field, then that gives you a lot of confidence, or gave us a lot of confidence that this is real and this is something that needs to have sort of our attention come to it.
So now that the project is over, can you talk a little bit about some of the conclusions that you drew from it?
Yeah, definitely. So we had 3 big parts of the puzzle that we ended up settling in. The first is infrastructure. What are the pieces of computational infrastructure that need to be built in order to assemble a data set that has sort of all the components that we want? So we said, there's all this data that's being taken out there, and that's really great. The problem is that it's all spread out. And there's no good way that you can take the data set from one institution and merge it with the data set from another institution and get something that's bigger than the sum of the parts. The whole goal here is to make the data more accessible and to make it easier to use. And so what we found is that there's a lot of systems that are trying to aggregate that data. Most of them are not particularly effective, either because they're not big enough or because they don't have the technical capabilities to handle like the bigger and bigger data sets that we get that are associated with things like genomic sequencing. And so what we said is that, look, there's no single system out there that we've seen that's going to solve this once and for all. And moreover, we don't see anyone who's working in this space who has such a critical mass of data behind them that they can solve this problem. And so we said that's something that the government should take a lead on. Building the computational infrastructure, like the servers and the databases and the connections and all this sort of stuff, so that people can actually just like store and maintain the data in a way that makes it as useful as possible to other people. And there are some various technical aspects of what that means. And there were some pilot projects that we were really, really impressed with and we think are a good step in the right direction. But saying that should be a major, in the same way that the federal government built the highway system and just said, like, this is a public good and we're going to do it. We said, like, do the same thing with computational infrastructure for doing data science on medical data.
Got it. So although there are some large companies out there that might be fairly well poised to do this research, like I'm thinking companies like Google or whatnot, the incentives aren't necessarily entirely there. What we need is some sort of federal funding for such a large project, because otherwise it might not get done.
Yeah, and I mean, it might be that like the underlying infrastructure, there could be a role that Google or Amazon or somebody like that would have to play in terms of where these computers actually going to be.
Right. Yeah, but it's very easy to throw something up on Amazon's cloud or something like that, and the government might choose to do something like that.
Well, and the other thing about the cloud that's nice is that it has a better track record of continuing to evolve and to grow as the demands that you place on it expand, because we know the data sets that we're dealing with right now are gigantic and we can barely handle them. Imagine where we're going to be in 10 years when genomic sequencing is something that you can do for $100 or whatever. So Yeah, thinking about the technologies that are not just the technologies that are going to work today, but the technologies that are going to be able to evolve so that they work still in 10 years. Like that was something that we were really thinking about.
So infrastructure is number one. What's number two?
Yeah, number two is, so imagine you have your beautiful database. It is ready for the data to come in. You have, say, lots of processing power that's attached to it so you can run the really computationally intensive machine learning algorithms. Great.
Right.
You need to get the data in there.
Aha.
And this is
Wait, is this like get the data in there technically or get the data in there like legally?
legally. So, yeah.
Oh, this is interesting. So a lot of the problems that we see in the technical world are not actually technical problems. They're either social problems or they're legal problems. And I guess legal problems are kind of a subset of social problems. They're problems that are imposed on us by humans as opposed to by sheer like mathematics or sheer computational ability.
Yeah, I mean that's the world that we live in with this one. We
Yeah.
call this data sharing. So there's two big aspects of it that we think need to be fixed. Number one is that there's a set of privacy, security, confidentiality laws surrounding medical data, which is totally appropriate, and we should not be cavalier about people's medical data. On the other hand, these laws, I'm thinking primarily of HIPAA, but there's actually a lot of them, and they operate on like the state level, so you potentially have 50 different sets of problems that you need to solve.
Ooh, yeah, that's rough.
Yeah, and these laws they're very difficult to interpret. They're very hard on hospitals and medical providers in the sense that they assign a lot of liability to those people if there's breaches of medical data. And they were written in the 90s. Like HIPAA was passed in 1995, and it hasn't done a particularly good job of keeping pace with the realities of, what big medical data means now, especially since after the Affordable Care Act, we effectively had something like, before the Affordable Care Act, there was something like 10%, 20% maybe, of medical records that were electronic. And now we're past 75%, we're something like 80%.
Oh my gosh.
And that was because of the Affordable Care Act. And so we just have this explosion of medical data that the laws haven't kept up with.
And so before, medical data was more for individual patient cases, like, oh, what does my file say? Whereas now the opportunities are much more numerous and potentially much larger as well in terms of like solving some of the diseases that we face.
Well, yeah. So you have this wealth of medical data that's locked away in EMRs, electronic medical records, or sometimes you hear them called EHRs, with electronic health records. And yeah, if you can aggregate that data, keep it anonymized, keep it de-identified, which is tricky.
That's a problem in and of itself.
Yeah, it really is. But let's say that you have a good privacy algorithm that is, or you have some differential privacy protections, or there's ways that you can protect people's
Right.
confidentiality about this stuff.
So imagine that's a solved problem.
Yeah, so it is and it isn't. It gets really tricky really fast, and I'll tell you
Right.
why. Is because there aren't very solidly enforced standards about the way that this data is formatted and what data is taken. And this is the second part that makes data sharing really difficult is, and I mean this both in the sense of like what data is taken, how is it formatted, and also as technical standards, like what's the literal file format of these files, so that if you have the medical records of Northwestern and the medical records of the University of Chicago, those hospital systems, and you were to somehow get them to agree to put them together into one system, if they're using different software systems, if they have different configurations, then it's entirely possible that there wouldn't be a good mapping from those data sets onto each other. And so you're not going to be able to make that sort of master data set that has everything in it, because they're always going to have these weird inconsistencies.
Right.
There's going to be columns that's missing. It's just a mess.
Yeah, or there's a column for, let's say, one feature in one data set and the same feature in another data set, but they collect slightly different information. Like maybe this collects it, this one data set collects it in a particular way, and this other one collects it to a slightly different standard.
Oh,
They
yeah.
define terms a little differently. So it's not just like the file format is incompatible and you have to reconcile that, but it's like the stuff that you're collecting could just be incompatible.
Totally. This happens all the time. I mean, we were talking to a lot of researchers, and they said one of the things that makes it really hard, like here's a really simple example, is let's say you're running a research study, and one of the things that you collect from each patient is their age. What age is that? So here you want to say, okay, what's their birthday? That would be the easy thing, is what's their date of birth. And you start to run afoul, well, not afoul, but it starts to become really tricky very quickly if you collect their exact date of birth, because that can be used to identify people very quickly. Your birthday is usually pretty unique. And so what they'll say instead is, what's your age? And it's like, okay, so is this your age when you were diagnosed? Is this your age when you're taken in, for this round of treatment? If you're relapsing from previous episode and that episode was 3 years ago, what age do you put there? And so it starts to, you think like, how old is this person? Can you think of something that could be a little bit more straightforward? But immediately you realize that, and there's no like strictly held convention on what we mean by people's age. And so people do what makes sense, within research groups, they're usually pretty careful. But these are the kinds of things that then when you go to try to combine the data sets, it can get really, really hairy really quickly.
Right. Now you've got noise in your age that's at least within a year, but in some cases, like you said, could be more than that.
Yeah, and this is challenging. Like, if you don't fix these problems, and this isn't just about, age, it can be things like, how do you identify certain genetic markers in a genome, or how do you say what a successful outcome is of a patient treatment? We heard one story about there was this physicians group that was or a hospital that was trying to define like a successful outcome so they could keep track of it for their internal metrics, and it took them 18 months to decide what a successful outcome was. Yeah. So, but the other thing I was about to say is that there's this whole issue that surrounds this called data harmonization. And that's explicitly the idea that you might have data sets from many different sources, each of which has their own, what they call batch effects, their own special characteristics that are just signatures of the way that the data was collected or that it was processed. And those batch effects can sometimes have a bigger magnitude, a bigger effect on the outcome than the actual effect, like the treatment effect that you're trying to study. So, these aren't like minor issues. These are issues that can potentially destroy, the ability for you to actually get any scientific insights out of your research. So it's a really big deal, and it's really hard.
Yeah. So infrastructure is number 1.
Yep.
Data sharing is number 2.
Yep.
What's our third?
Our third is what we called people and skills. So imagine you have your gigantic, beautiful computational infrastructure. You've addressed some of these like legal and standards concerns so that you can get the data going in there, or you can get people to be able to like access each other's data through this system. The third thing is you need to have people who are capable of using that system and who have the skills that we need to actually get the insights out of the data. And so we were thinking of this in 2 different ways. One is there's kind of a lack of bioinformaticians, biostatisticians, these kind of biologically educated data scientist types. There's a lot of them, but there's just not enough to keep up with the demand of the research that needs to happen in this field. And there's also a lot of people who are not technically trained and realistically, probably never really will be. It's not within the realm of what they're working on. I'm thinking of maybe your more traditional, biologists or nurses or doctors. These are people that we shouldn't ask to become computer scientists so they can work with the data. So that means that it's up to us as the technical people in the field. Well, us, the people who are working in this field as statisticians and as software engineers and things like that. It's up to them to build tools that are accessible and that actually get the data out and, deliver the insights to the people who are actually on the ground and need to use those data-driven insights, hashtag to actually do better, deliver better medicine.
Got it. So infrastructure, data sharing, and
people and skills.
People and skills. Do you feel, actually, first of all, I should ask before we close out the episode, where can people find this paper? Is it available for free?
Oh, yeah. So we wrote about a 30-page white paper And this went to the vice president and a number of other people who were associated with the Moonshot. This is available on the Civis Analytics website. They'll ask for your email just because they want to keep track of who's downloading papers from our website, but it's totally free. And there's also a series of blog posts that I wrote a couple, and then one of my other, my colleagues on this project wrote the third one, where we broke out each of the sort of 3 big planks that we talked about. So you can also check those out, and we will have all the links in the notes on our new website, lineardigressions.com. So go check that out.
Fantastic. And I guess my last question for you is, when you started this project, you probably had some kind of mental understanding of how involved it would be and perhaps this size or the scope of the project. How did that mental model change as you went through the project?
That's an interesting question. Well, I think we came in not realizing how much work there was to do, not for us, but for the field. We thought we would come in and we would talk to some people and realize that there were 3 big data sets, and we just have to figure out how to unify those data sets. And we would, tell them a little bit about the wonders of databases, or I don't know.
Yeah.
And
it would be a more tractable problem.
Yeah, that was really, really not what we found. It's very confederated and decentralized, the work that's being done around cancer. And it's getting better. There's, I think, a lot of recognition that that's not the most effective way to do this work, but it's just really, really hard to build this stuff. And if it had been that straightforward, they would have done it already. And so, yeah, there was low-hanging fruit in the sense that everyone we talk to says, yeah, we're going to need reforms of the legal regulations, and yeah, we need more people who know how to do biology and computers. But actually saying, how do we accomplish that was really hard. And I think the other thing that we maybe didn't anticipate was when we started, we were like, okay, so we're going to do some interviews, and we're going to get the lay of the land, and then we're going to write a report, and And at a certain point, you realize that you're just never going to be able to get everything. We had a few months to put this together, and obviously there are tens of thousands of very smart and dedicated people who spend their lives learning how to do this. So of course we're never going to be able to capture all of that. But it was very humbling to get a sense of the scope of the work that's going on. And I think at some point near the end of it, we counted up all the interviews that we did. And, I think these were even just the formal interviews that we took notes on. We had probably many more informal interviews besides, but we were at almost 50 by the time we were done, hour-long interviews.
Wow.
There's just an incredible amount of stuff that's going on out there. And every one of these interviews, you learn something new, and you get a more nuanced idea of why this is hard. Like I said, if it were easy, they would have fixed it already. So it was simultaneously really difficult, but also, as the data scientists in this conversation, most of the other people working on the Cancer Moonshot are cancer researchers, and us as the people who are kind of observing from the outside and saying what it seemed like made sense to us, that was a really empowering position to be in, to have this very broad view, and to, sometimes feel like we could walk into a room and say something that honestly might upset some people sometimes about, these are things that don't really make sense, and you're spending a lot of money on these programs, and sometimes they don't seem like they're going to work as well as some of the other programs. And
right.
But feeling like we had the freedom to say that because, we had this very broad view, and we also sort of had the data credibility to back it up. One last thing I want to add before we wrap up is, so this team there were 5 or 6 of us at Civis Analytics who were working on this. But one little piece of trivia from inside of our project is, on the first meeting that we had, we all downloaded a bunch of papers, and we came up with a plan of attack for our work. And then we went on Amazon and we bought a cardboard cutout of the vice president. because
Yes.
this is his project. And so we have a cardboard cutout now that lives in our office, and he came to every single one of our meetings. And so
Did he say anything?
he just stood there smiling at us. He was like our fourth musketeer, so to speak.
That's amazing. Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.